Good afternoon, everyone, and welcome to my 2024 TED Talk presentation. First of all, who in here has been stuck in a traffic jam before? Please raise your hand. Yeah. So, especially if you live in a big city, this is going to be a problem, and it's a problem that is very unnecessary. Like we have stuff to do, we have places to go. So stuck in the traffic is never really a good problem. It's never really a pro situation in any situation, right? So sometimes when you get stuck in a traffic jam, you get very angry, and then you get into a road rage incident, right? And something like this could happen, where a car crash, or even sometimes someone crashes into you, right? And even sometimes, rare occasions, not rare in some countries like Thailand, where road rages happen a lot and people don't know how to drive, you end up killing other people, or someone else end up killing you, right? So my question is, how can reinforcement learning be integrated with the traffic system? So before we get any further, what is reinforcement learning? Reinforcement learning is just a subcategory of machine learning. So the main idea of machine learning is that you want like a machine or the computer to do tasks for you that you could potentially not do yourself. So the background of this is you give the machine information and data, and then you tell that machine what to do with the data, and then after some time, you program it some more, it gives you an output, right? So what kind of tasks can machine learning do? So it can do tasks like analyzing, classification, predictions, and a lot more based on the data you give them. And an example of this is the AlphaGo program, right? So what we have here is the game of Go. Go is one of the world's most ancient board games, right? We don't even know to this day when it was invented. Is it really that old? And it is one of the hardest game to, if you're really at a high level, it's one of the hardest game you can ever beat someone, and especially someone like the #1 in the world. This guy Layne, he's from South Korea. He's was previously the world #1 Go player. So, and this AlphaGo program is a reinforcement learning program, and was able to beat the world's #1 Go player. So the main idea of the game is pretty much you try to surround the other pieces. So if just pretend you're a black piece, and if you got all the white pieces around it, you are able to capture that piece. And how you win is how many pieces you have captured in total. So from this game of how big the board is and how simple it is, actually makes it really hard to beat if you're actually really good, because there's many possibilities and very high outcome, high possibility of outcomes, right? There's a certain degree in chess, where there's a limited space and limited pieces, what each pieces can do. In a certain time in chess, there's only a few possible best moves. However, in Go, it is much harder. So it takes a lot more work for the AI to actually analyze the data from the board and actually able to beat the world's #1, right? So what is reinforcement learning? So reinforcement learning consists of an agent and an environment, and there's this thing called the action, state, reward, where I'm going to get into, but the two primary factors of reinforcement learning just consist of the agent and environment. I'm going to explain that in the Bonds way. Let's just say that you're at the MI6, right? The MI6 headquarters is pretty much the environment in the model. So the environment is just pretty much the place you're doing your task at, right? So then you have your agent, Mr. Bond here. So MI6 tasked Bond with killing a terrorist group, for example, right? So he is the agent. We task him to get rid of a terrorist group somewhere. So then he try to kill, he finds that terrorist, right? And in the first try, he might have gone with a knife or something, and he fails to kill the terrorist. So then he goes back to M, which is his boss in the movie, right? But so anyway, he brings M the report back of his of his failure. So that little report would be considered the reward. So it's pretty much the output of the first try, if you will. And then M will probably give him like a pistol or something better to kill people with, right? So then that reward goes back to M, and then M tries to find a solution, and then gives the agent back a better solution, right? So then James Bond goes back again to finally kills the terrorist. So in reinforcement learning, there might not be able to complete the task in the first try. It might take 2, 3, or even sometimes like hundreds of times. But how do we actually implement that with the traffic system, right? What we have here is just a reinforcement learning program called libsignal, right? So instead of having your agent try to kill a terrorist, we have our agent trying to fix the traffic. So this pretty much is the same layout as a simple layout of reinforcement. It might look confusing at first, but what we have on the left side is our environment. So this is pretty much a map generator, or you can import your own maps. So let's say you're trying to fix the traffic of LA, you would import the map there, right? And then we have our setup command. So this is where we organize all our files, and then this is where all the coding happens, really. And then, of course, we have our agents, right? And then that agent is trying to fix the traffic inside the real world in the map, and then that map, that world, outputs back a thing called the reward. So that reward is just the data from the training, and that reward goes back into the training to make itself like train better. So similar to how M helps out Bond by giving him like a pistol, this one gives from that reward, it gives back to the agent a better training to do. So then, what are we actually trying to fix? Like, what factors do we need to consider like that we're actually fixing traffic? One of the factors is the queue length. As simple as it sounds, it is pretty much just the length of the traffic, if you will. So if, let's just say in scenario A and scenario B, in scenario A we have a 20-meter long traffic, and then in scenario B we have just a 2-meter long traffic, so just like about like 2 cars. The scenario B will be much better than scenario A because the length is shorter. It's very simple. And the next one is called the throughput. The throughput is just simply of how many vehicles it is in a certain area. So let's just say one intersection has 4 cars and one intersection has 40 cars. The one with the 4 cars will be much better than the one in the 40 cars. So as we're going through the training, what we can determine is how many cars is in the area at a time. So we can determine if it's actually the traffic is actually fixing itself or not. The third thing is the travel time. So let's say you're in scenario A and scenario B. In scenario A, the car going from point A to point B takes around 30 minutes, and in scenario B, the car going from point A to point B is 30 minutes. In the other one, the 30 seconds one will be much faster than the 30 minutes one, of course, so that means in scenario A is going to be better than scenario B. So then, how are we actually going to implement these things, right? These reinforcement learning. So, of course, we don't have access to the real world. Like, we can't just go to the public, public roads and try to do our stuff, reinforcement learning stuff there, because people have to do their things still. So that's why we use a simulation program. And in my case, we use 2 simulation programs. One is called Sumo and one is called CityFlow. So what we're trying to do is we're trying to get the best result as possible. So instead of using 1, we use 2 to maximize our results and to make sure that everything is working the way they're supposed to work, right? So in these simulation programs, there are many scenarios we need to consider too. So like when we're doing tests on like a 1-by-1 like intersection, for example, that might not apply to a very messy intersection like the one we see right here in the Cologne city. I believe Cologne is in Germany, it's just a city in Germany. And so we have to test it out in different scenarios because many countries or even in continents, the road system and city layout is not going to be the same, right? So in cities in Germany and city in Lagos, Nigeria might not be the same. Of course they're not the same. That's why we need to test out in these different scenarios. So if you're wondering what the simulation looks like, here's just a one-by-one intersection. So in this program, in Sumo, you can actually randomize all your throughput and your average travel time to cars to test out different road systems and city layout. So after the training, after all the simulation has been done, we still need to understand what it is that is looking at, what is the reward it's getting, so what kind of data is it reading. And just like the MI6, there's not only Bond in the whole MI6 headquarters, there's many agents you can choose from, right? So one of them, for example, is called IDQN. So this agent, it is reading the lane vehicle count. So what data it is receiving is in the lane that the car is not moving, so the lane that is stopping at the moment, it is getting the vehicle count of how many cars there is in that lane. And that data it receives goes back into that training. So then we go to the next slide where it talks about that same agent. We can see from that agent that's its method of trying to fix the traffic, of getting the vehicle count on the waiting lane. You can see that the average travel time in each episode is just another word for time of training, right? So we can actually see that the average travel time has actually gotten decreased. And for all these graphs too, it is telling pretty much similar things, but in different scenarios. So this one is a 1x1. We tested out in Cologne, 1x1 city. Tested out in a 4x4. And as most of them have a trend of the average travel time going down. And in the table on the right-hand side, we can actually see that it's not only the average travel time, we can actually see that in this one, for example, this scenario of city flow 1x1, the IDQN method, the agent works the best in this scenario, not only in the travel time, but in queue and delay. So, and as you can see, a lot of these are actually IDQN, but it's not the point of me showing this that IDQN is the best method. The point of using machine learning to back up the reinforcement learning too is that we actually don't need to know which method works in each scenario. So what's cool about that is if you want to implement this into a random city in Ulaanbaatar, Mongolia, where you don't know the road system, right? You don't know the city layout, you don't know how the road system works at all, like the rules, everything. If you implement this, right, you wouldn't know which method you would be using for that city. However, with machine learning, it can train itself and it can decide which the best method to use at that scenario. So it would be very helpful if you don't actually even know what these does in the first place, but you just use machine learning, and as it trains itself, it comes up with the best solution possible. So what is it not considering in this model specifically? In the lip signal model, this reinforcement learning model is not including different scenarios like bad weather or car crashes, the very thing we're trying to fix or we're trying to avoid. So let's just say we implement this into Ulaanbaatar, Mongolia, where a city where we don't know anything about. What if that city was snowing that day, snowing very heavily, or a sandstorm just came in the city and just blocked all the roads? The AI model wouldn't be able to actually understand the situation very well because it hasn't been trained that way, right? So it's not really considering that scenario. Or even a car crash. So if someone just crashed just in that same city, it is not considering the fact that there's a blockage in the road at the moment. So the AI model, this AI model specifically, is not really accurate for doing that. But however, with that in mind, there is still many other researches being done at this moment from doing this exact same thing with reinforcement learning and trying to integrate within the traffic system. And by this point, who knows, maybe someone else has already came out with a new model that actually includes the traffic system at the moment. It's not really a big deal. It's like, I mean, it is a big deal for traffic, of course, like when there's a crash or there's bad weather, but for AI to learn, like you can just train the AI again to learn about, not to learn, but like to train them to know about the situation of like different scenarios like snows and car crashes on the road. So that's it, I'm done.